Sorry about that, I had a student. Here we can continue on this. 12, 16, that was plus the 64, plus 32, it will give us what? 12, 48, and plus 16, it's gonna 48 plus 16, 54, 12, 64. That was plus 16, 32. Plus 8, 12, 72, plus 5, it's going to be 12, 77. So this number, binary number, in decimal, it's going to be 1277 decimal. Octa, hexadecimal. This is converting between all those bases. Remember why we use binary. Binary is the machine language. Why do we use decimal, our language? Hexadecimal, it's really better for addresses. If you want to read an address as well. Usually you see this in addresses. F, 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 2 or F, A, 1, A. Those are addresses. Think of you, so this address as binary. Why is it going to be binary? Very quickly, binary is 111 F. For E, what is it? 1110. For 1 is 0001. For A, it's 1010. So this hexadecimal number in binary is that number. Looking at it, which is easier to understand. For sure, it's this one. So now we took representing how to represent decimal numbers, which are integers. This is representing decimal or positive integers. Sometimes they add a 0 for the sign because it's positive. Now let's take a quick review how they represent what? Negative numbers. Remember, this is all data. So how to represent negative integers, all numbers. Example, negative 25. This is in decimal, our language. There's 3 ways. There is what we call sign representation. Let's make them 1, 2, 3. One way is the sign representation. Sign representation, taking the most significant bit, adding 1 bit for the sign. 0 for positive, 1 for negative. So I know negative 25 is going to be what? The sign is going to be 1. So let's see how to represent 25. I have, first of all, take the 25 by itself. How did we represent 25? Decimal. Earlier, I can do what? I can divide by 2 or put 1, 2, 4, 8, 16, 32. I don't need the 32. Why? It's greater than 25. 25 is 16. 8 is 24. 0, 0, 1. This is 25. And usually, don't come and put the 1 here on the 32. Usually, I'll take, how many bits is this? 1, 2, 3, 6 bits. I have 7. A byte is what? 8 bits. So it's gonna be, this is gonna be for the sign. The 8 bits, which is the most significant bit. Most significant, the one with the most significant value. A byte is 8 bit. So I used 8 bit. 1 for the sign, 7 for the number itself. If I used a word is 2 or more bytes. 2 bytes is what? A byte is 8 bit, 2 bytes is 16 bit. So to represent negative 25 in a word or 2 bytes, I'll have what? 1 0 0 1 1 0 0. This is how many? This is 7, 8, 9, 10, 11, 12, 13, 14, 15. The 16 bit is going to be what? The sign. This representing what? The sign of the number, and this is the range of the number itself. This is negative 25. This is using the sign representation. One way sign representation. The problem with this one, if I told you to represent the negative 0 or positive 0 and negative 0 in 1 byte, in 8 bits, 6, 7, this is the positive 0. This is for the sign, and this is for the number, and negative 0, this is positive 0, negative 0 is what? 7 zeros. And those two are 0, have the same value. And this is what? I have 2 representations for the same number. And this is what? This is bad. Why is it bad? Because computers, this is what I say, computers are dumb. They can't do anything you don't tell them. Though, if you remember World Economic Conference, they were talking about artificial intelligence. What's artificial intelligence? Computers making decisions by themselves. This came out at the beginning of 2000. It was a good research topic. Some people start digging in it, but then it died for a while. Then it's coming back now by Google. They use it a lot. They use it in prediction. They can do now anything you're doing by your search engine when you're searching Google. So we took the sign representation. Sign representation, 1 bit for the sign, most significant, and the rest for the number. And we said if I'm using a byte, 1 byte, I'm going to have 7 and 1. This is the sign representation. Yep. If I'm using a word, which is what? One for the sign, 15 bits. For the number, and we took examples on that. Second way was what? The 1's complement, and they usually write it this way: 1's complement. 1's complement is what? What's the negative 25? I find the 25 same way I did and the sign representation. Here's 1, 2, oh, what was it? 25, 16, 32, 64. It's gonna be 0, 0. I added those. I want to make it an 8-bit 0. This is 8-bit. It's always better to take them as byte. The 1's complement is flipping every 1 to 0 and every 0 to 1. This is the 1's complement, or the negative 25 in 1's complement. In 1's complement. Negative 25 in 1's complement. So I added those. This is better. Third way was, it has the same problem, negative 0 and positive 0. Try it out. The 2's complement. The 2's complement. It's we're doing it for the same one, and the 2's complement. We find the 1's complement first. And how do I find the 1's complement? I flip every 0 to 1 and every 1 to 0, and I add 1 to the 2's complement. And by adding this one, this solves the problem of the negative 0 and positive 0, which means having two representations for one number. And be careful, we don't use this. I found the 1's complement. The 2's complement is finding the 1's complement plus 1, and I add 1 to it. Here's this 1, 1, 1, 0, 0, 1, 1. This number is negative 25 in 2's complement. That's the way they write it. Sometimes this is how to represent negative numbers. Sign representation having 1 bit for the sign. 0 positive, 1 negative, 1's complement, where I flip every 0 to 1 and every 1 to 0. 2's complement, I add 1 to the 1's complement. Hopefully this was good enough. Now let's take a small example and show you how this works on a computer level. Now let's say I have 25 minus 9. What does this equal? It equals 25 plus negative 9. If I find the 2's complement for negative 9 and add it to 25, that should give me that should give me the same result. Let's find the 2's complement for what? Negative 9. And let's take them in what? In 8-bit. So 9. How do I find the 2's complement? Find the 1's complement and add 1 to it. What's the 1's complement for 9? What's 9 first? 1, 2, 4, 8. This is 9, and I add 4 zeros to make it 1 byte. Now flip. This is what? The 1's complement. We said we had a problem with it. Well, the positive and negative 0 having two representations for one different number. Negative 0 and positive 0. Now what's this? I add 1 to the 1's complement. Binary addition. 1, 1, 1, 0, 1. This is what? Negative 9. Is it really negative 9? How can I know? How can I check? So here I can go there and do it. What's 25? Let's move it a little bit here so I can have space. What's 25? 25 is 1, 2, 4, 8, 16, 32, but I don't want this 32. 25 is making it 8 plus what? Negative 9. I'm doing 25 plus negative 9. Negative 9, I got the 2's complement of it. So 1, 1, 1, 0, 1, 1, 1, 1. What does this equal? Let's see. This equals 1 plus 1 is 0. It shows, yeah. And I have, let's take that one out. So we know, what do I have? I have a carry of 1. 1 plus 1. I have a carry of 1. Let's put the carry in red there. And now I have 0 also. 1, 10, 0. And this is gonna be 1 and 1, 0. And I have an overflow. Why do I keep putting it in there? 1 and 1 plus 1 plus 1. This is gonna change to 1. And I have an overflow of, or carry of 1. This is gonna be what? 0, 1, 0, 1, and I have 0 and 1, which is gonna go to the flag register. What's this? 1, 2, 4, 8, 16, 32, 64, 128 is what? 16. 25 plus negative 9 is 16. What's up, Daniel?
What are you doing?
What? Why I leave?
You have a YouTube channel?
No, I'm gonna start putting them on.
Oh, really?
Yeah.
On YouTube?
Yep.
Oh. I said people made a lot of money with YouTube. That's what I said on the show. Like how much video have you have on YouTube to make money on YouTube?
I don't know. I'm not making it, doing it for money. I'm doing it easier for me so I don't keep giving you reviews.
Oh, yeah, you're right.
So I'm gonna put assembly, C++, some security, some.
Just send the students to your website.
Yeah.
Yeah, it's way better.
So now where did we stop? 25 plus the 2's complement, and if you see, it gave me 16 by using the 2's complement. And what I did here, in adding binary, 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 1, what I used is 0 with a carry of 1, 1 plus 1 plus 1, where I had it here, I'll have 1 and a carry of 1. Those are basically covers all of the possible situations. And remember, this goes to a carry to the over flag or overflow flag in the flag registers. I only have 8 here, and we'll talk later about the flag register. Now let's go to the problem of positive 0 and negative 0, which we had in the sign let's see, is positive 0, 8 if I want it, is 0, and here's negative 0. 1's complement we flipped. It's not the same. Add 1 to it to find what? The 2's complement. I have a 0 here. It's going to give me all 1. It's going to give me all zeros with the extra one that will go to the flag register. This representing what? Negative 0. What's positive 0? Here's the positive 0. So I'm having the same number. In 1's complement I had a problem. This is negative 0 and 1's complement. And if I wanted the positive 0, it would be 8 zeros in 1's complement. Two different representations for one number. In this case, I have it what? Fixed in the 2's complement by adding the 1. Solves the problem. This is how the problem was solved in 2's complement. So we took how to represent unsigned or positive numbers, signed representation, negative numbers, 3 ways, signed representations, 1's complement, 2's complement. Now how do we represent characters? We said characters can be represented in 3 ways. ASCII, American Standardized Character, something, ASCII, 2 to the power 7. They use 7 bits for any character. And A was represented in 65, let's say, decimal, which is 1, 2, 4, 8, 16, 32, 64, that's 7. This is an A, capital A, having a value of 65. 2 to the power 7, having a range of 0 to 127. Extended ASCII. They added 1 bit for the range, so I'll have 2 to the power 8. This here I don't need the 0. Sorry, this is 7 bits. ASCII, the extended ASCII, they added 1 more bit, meaning having 2 to the power 8, I'll have from 0 to 255 possibilities. 0 to 255 characters. Both of them weren't enough to represent what? Other characters. For example, we have Arabic, we have Germany, we have Chinese. I don't know, I think Chinese, they use symbols for characters, and I think they have about 1,500 symbols. So can we represent the Chinese in any of those? No, so they came up with Unicode. Which uses 2 to the power 16, meaning I can have 65,000, how much was it? Unicode 65,356, I think, or 536. 65,000 plus characters, let's say. 65,000 plus, and that was fortunately enough to represent any possible language in the world. 60 Unicode, 2 to the power 16, meaning 16 bit for every character. Extended ASCII, 8 bit for every character. ASCII, 7 bit for every character. So this is, we took representing characters, representing numbers, negative numbers. We have still how to represent floating points, and we can explain that using the 40-bit simple model. And okay, 32. Let's stop this one. Here, stop.